right. So last session of this workshop, thank you for staying with us so far, is from a group of students, PhD students from the Institute of Digital Games, starting with Marvin Zammit. Then we'll move on to Roberto Gallotta and finishing with Matthew Barthet. Marvin has been working while he's sharing his screen, or he's trying to share his screen. I can talk a bit about Marvin. Marvin is like in his final year, actually working on his thesis right now. He has been working on this system he calls LLM. It's basically, by the name, as you can figure out, it deals with a bit of large language models, a bit of crawlers, dungeon crawlers when it comes to game design, and he has been working in the part of retheming games using large language models for retheming games. And here he is today to tell us a bit more about his fascinating work. Thank you, Marvin, for being around. The stage is yours.
Thank you. Hello, everybody. My name is Marvin Zammit, and I'll be talking to you about the work that we carried out on Crawl LLM, a generative AI pipeline for retheming games. So our objective for this project was to utilize generative foundation models, LLMs and Stable Diffusion mainly, to generate a different theme for a game and create all relevant assets required to reskin it and fit this new theme. We wanted to keep the game mechanics fixed, but change various visuals and text parts. Some other work that we saw in this area all required some kind of human intervention to format or assemble the generated assets, but we wanted to see how far we could push the automation of the pipeline. So we're looking into having everything in the pipeline generated, used as is in the game without any further intervention. The only input that is given is a textual description of the theme that we want. We made this given semantically in the form of setting, environment, epoch, and visual style. And from then onwards, the LLM takes over. As a note, the LLM can also generate these since it is text-based as well. So we wanted again to act as a test bed for this study, so we created Crawl LLM. It's an original game made in the Unity game engine, and it combines dungeon crawling, which is presented as an abstraction of a top-down view, as you are probably commonly aware already, with some components shown from a frontal point of view. We also added card-based combat, which has a more concrete representation of the visuals. We selected this to have a variety of assets and to test our pipeline with. And here we can see the different assets, the different individual assets highlighted that were generated by the pipeline. We also generated the levels procedurally at runtime, although that was by a constructive method, not through foundational methods. The dungeon structure and layout, in fact, have been based on Joris Dorman's cyclic dungeon generation, which is used in his unexplored games. They generated dungeons functionality through a cyclic structure with multiple subcycles, generating lock and key puzzles that feel more organic. For the layout, each subcycle was mapped to a different thematic location that the LLMs generated, each having its own visual, having its own visual themes and enemies. The gameplay structure guided the construction of prompts for the LLMs to generate new themes, stories, characters, and locations, which then directed the generation of corresponding visual assets. This approach enabled the game's aesthetic to emerge from its underlying narrative. The orchestrator of the generative pipeline is the LLM, for which we used Mixtral 8x7b. It was small enough to run on unlimited resources, but large enough to give decent results without hallucinations. The different elements are generated in a staggered fashion, as can be seen from this flowchart. we start off from the semantic theme descriptors, and we move on to the basic game details such as the game name, intro and outro text, and so on. And we move on to generate 5 locations with their descriptions and the different descriptions of the different environment elements within, and also the enemies which are themed to that location. For image generation, we follow the similar structured sequence, and it feeds stable diffusion XL model with descriptions generated by the LLM, together with predefined guides that define the constraints required to plug the assets directly into the game. For this purpose, we used a control net models based on pose, as you can see, and also on online sketches. So you can see, in fact, on the right hand side, we have the character animations defined by poses, show from the front, side, and back, and we have the outline of the cards, and also the tile set outline defining the positions of the doors, walls, and floor tiles, so that they can be plugged in directly into the engine. This is an example of the dungeon tile set generation. We follow again a multi-stage approach, with first feeding in the prompt with the floor descriptions, together with the guides for the tiles. Then we extend the image with noise for the full feed the full guide to the control net, but also mask the areas we want to draw walls in. We repeat the process with the door masks finally, and the door descriptions to complete the tile set. A similar approach was taken for the sprite sheet generation. We first generated the side-facing sprites using side poses and the textual description. Then we add the side poses and generate. Then we add the front poses together with the already generated poses, and repeat the process to generate the back-facing poses, and we can then automatically compose the full sprite sheet. So, in summary, the study explored the application of LLMs to orchestrate game reteaming through generative AI. We created an original game, which was Crawl LLM, with dungeon crawling and card combat mechanics to test our pipeline. And this work has been demoed last year at the conference on games. And since then, we are also working on human evaluation of generated assets, and also taking this process further by having an iterative improvement cycle for the assets to try and improve coherence, thematic fitness, and diversity. Thank you for your attention.
Thank you so much, Marvin. We can. I will observe the chat. There's no question so far, so I guess we can move on to the next speaker, who is Roberto Gallotta. Oh, there's a question from Mike Cook. So since it just arrived, maybe you might want to take it. So Mike says, "Are the games playable online?"
No, currently they are not.
But the demo.
For the demo, they were playable. Yes, we just haven't put them up on a public website, because we do have a web player. Actually, we did deploy these.
Exactly. So what are the plans before or soon after the PhD? Are there any plans?
I guess after we publish the paper, we can also put. We have a paper currently being reviewed. When the paper is finished, then we can put the demo up as well.
Cool. So far, Mike, the only thing available is a video. It's a very cool video, though. So you need to look at it if you're interested. And it's a page about the project for now. Thank you so much, Marvin. Roberto, you are next. Roberto Gallotta is another PhD student from the Institute of Digital Games. Second or third year, Roberto? Please remind me.
Second, but it's gonna start the third now.
Second, so which means that Roberto has been very productive, because I thought he was third year, because he has been extremely productive in what he does. And one of the things he loves doing is to play around with LLMs and AI tools for designers. And he came up with this really cool name called LLMaker. It's an AI-based tool for designers that, you use it to co-create video game levels with LLMs. So the stage is yours, Roberto. Thanks for being here.
Thank you, Yorgos. Right, so yes, I'm Roberto Gallotta, and I'll be talking about LLMaker, what it is, how we come up with it, and what are the current research plans and past plans, obviously. So, spoiler alert, this is what it looks like. It's a application where the designer chats with a language model to generate game levels. And the property of the language model is that it has to learn, it has to understand what the designer wants to do, has to be able to interact with a backend system in order to create and edit these game objects. Why did we work on this, right? So if you look at tools where a human designer and AI collaborate to create levels or any kind of content, usually these have static graphic assets. And since they usually include a lot of buttons, sliders, menus, submenus, you have to learn how to use the tool in order to be proficient at it and actually generate something, create something that is interesting and playable, since we talk about games, right? With the rise of popularity of language models, we asked, what if we use just natural language? Can we actually do this? We could. So this is a video. I'm going to play it at 2x speed just for the sake of time, of the LLMaker application in action. So you can see that the user just types down what they actually want to do. In this case, create a room. The language model takes care of all of it. It responds to the user, and in the backend, it generates the game content, and we have a stable diffusion pipeline to actually create the graphic assets. This all works under domain constraints for a game that we are also developing. And yeah, I mean, kind of talk too fast here. But yeah, you can create rooms, you can add enemies, treasures, you can connect rooms together with other rooms. Through corridors, you can add traps, and there are different properties of the game that you can look. And obviously, all the graphics are generated in real time, so this is going to take a while. But yeah. Okay. Let's now talk a bit more about all of this. If you could just... There we go. So, how do you get to actually generating game content using language model? What we do is, instead of generating text that is unstructured, we try to generate text that is structured. So we move on from just natural language to our JSON representation of the game object, let's say, or a YAML, depending on what you need. And these have to respect constraints of the domain. So if you have, for instance, a maximum HP allowed for your enemy, you cannot generate values that go over it, because that the level would be invalid, right? So this is roughly the flow that we have. We have a user message with a request in natural language, gets interpreted by a language model, and you get something out of it. When we were working on this, we wanted to find out which of the main prompting methods at the time were the most reliable, especially, and the fastest. So we analyzed methods of zero shot, few shot, chain of thought, and also function calling. We defined a set of metrics that we were interested in. So mostly we were looking at the reliability, the accuracy of our responses. So a response can either be successful, so we get a content that is valid, respects the domain, and also is what the user asked, which is not as easy. Or we have different levels of failures that we can run into, as well as also the speed at which we're getting our content back. And we evaluated all of these on a set of test cases that we developed, which reflect realistic designer requests that the human can make to the system. So as you can see, like make a room in a swamp, add a couple of enemies, and this can be a bit fuzzy. You don't have to be super specific. What we found when running all of this, we found that function calling was the only method that actually never incurred into parser or domain failures. And this is expected, but also it was the one that actually had the shortest response time, so lowest response time, sorry. So we were able to include this in an actual real-time application. We didn't have to wait a full minute before we got something back. It was very quick iteration, about 3 to 5 seconds at most. In general, however, we found that other prompting methods have different drawbacks. So it's not like we have to only use function calling. We could use the others, but there are different drawbacks that we must take into consideration. For example, while most of all of them actually incur into domain grammar errors, meaning they weren't able to remember exactly the rules of the domain, this was a year ago. New models are actually much better at keeping this in context, this context in memory. So maybe we can move on from function calling. For now, we stuck with this. We were very comfortable with these results. Also because other prompting methods actually take longer to give you content, the more complex your level is, because it's a longer text description that you have to pass. And this was just to generate game content. What about graphics? Well, we couldn't have predefined graphics, right? Because we have humans and LLMs collaborate, and they can come up with anything in the level. They can have, as you've seen, entirely different targets. They can make zombies as well as they can make ancient Roman legionnaires. We cannot use predefined graphics. So we wanted to automate this, and we did this by using Stable Diffusion with the inclusion of a concept called context, which in our case actually just means additional domain information that we pass to the generative model for more customized image generation. For example, if you have a room, you can extrapolate different kinds of details from this room and drive the generation of the same entity and get a vastly different sprite. So just to show an example, if there is no context, your sprite is generated just with its name and description. But if you have, for example, a background image, if you have a background image, you can, for example, extrapolate the dominant colors of that image, convert them into natural language, and then pass those to your Stable Diffusion model to better reflect where the entity is supposed to be in your game. So we evaluated about 50,000 unique sprites we generated with combination of enemies and rooms, and we evaluated them on different metrics. We evaluated them on diversity, so how different different sprites were according to the different level of context. Their quality, so the image quality itself of the sprite, the consistency, so the shared ratio of dominant colors between the sprite and its background, and the complexity, so how complex the actual image appeared. So we did that, but we also had human users actually evaluate a subset of these sprites on mainly two metrics. So just consistency, so human perceived consistency of the sprite with its background, and user preference, so whether they liked one or the other. When it came to results, I try to compress both of them here. We found that using some of the context led to a very high consistency, so high ratio of shared colors, but very low quality and complexity. And they were also disliked by the users. So even though they excelled at one metric, we had to discard them because users didn't like them. Looking at just users, they actually rated very high one of the context itself, which was semantics, so just including the name and the description of both the entity and the environment in the Stable Diffusion prompt, and actually were rated first for both consistency and preference. So in the end, we implemented that in LLMaker. So what you saw in the video was this context being applied. Takeaways. What we demonstrated so far is that language models can be used to co-create game content, as you've seen in the presentation video, and that we were able to automatically generate graphics that were liked by users and were rated as consistent with their surroundings. And unlike other tools, we showed that in this case, the only entry barrier that you have is just your language. As long as you can express your idea and the model is able to understand it well enough, then you're able to generate a level that is interesting and playable. That's all. Thank you very much.
Thank you so much, Roberto. Thanks for being on time. The language barrier is not an easy one to some, I'm just saying. You know.
I know.
But great stuff. Maybe there's a question here. Let's see. Okay, so Adonis did the usual thing of posting more information about your project. Thanks, Adonis, about LLMaker. If you want to know more about what Roberto is working on, check out this page and check out his papers. There might be more questions in the future, Roberto. Let's move on now. Thanks. Let's move on now to Matt Barthet, the third and the last speaker from the Institute of Digital Games. Matt is also a PhD student, completing his thesis as we speak. Matt has an interest at the intersection of procedural content generation, and affective computing. He has been playing out quite a bit with this idea. Today he's going to be covering, it's basically a paper published, the paper published a year ago, named Closing the Affective Loop via Experience-Driven Reinforcement Learning Agents. And it's basically, very well aligned with the aims of the OPtiMaL project. Actually, all the talks here are very well aligned to what we're trying to do. Matt, the stage is yours.
Thank you.
You're here.
Yeah.
Okay, good.
Yes, I'm here. Yeah, hopefully you can see my screen.
Yes, we can see
Yes.
everything.
Yeah.
Go
Thank
ahead.
you. Thank you, Yorgos, for the lovely introduction. Yes, I'm Matthew Barthet. So basically the core motivation of this work was this notion of closing the affective game loop, and we want to do that through reinforcement learning and experience-driven procedural content generation. In other words, what this formal statement means is we want to design like this end-to-end system that can detect the emotional responses of players and generate new content that elicits a certain response. So like the idea of generating levels that are very intense or very pleasing to different players. And in practice, what this means is that we can autonomously generate personalized content, again, based on the player experience. So I have a couple of examples here. My presentation is mostly going to be tackling racetrack generation. So I have an example of a boring racetrack targeted towards beginners, and then another example of our system generating like a very high intensity racetrack for expert level players. So it can adapt to different player personas. On a very like high level, this is what our approach looks like. It essentially mimics the building blocks of the affective loop. So we have this idea of eliciting emotion and behavior from players. We detect that emotion and we design levels appropriately. The first part that I want to focus on is actually the designer agent. So we use PCGRL for generating racetrack levels. Which algorithm you use is flexible. Here we use GoExplore because GoExplore, when we were working on this project, was proving itself to be very good in difficult tasks like the one we're taking on. But like I said, any algorithm like PPO and so on can work here. But essentially the designer, I have a video on the right, very slowed down so that we can see it in action, needs to select racetracks from, select components of a racetrack from a possibility of components like straights, curves, loops, and so on. And it needs to iteratively build a racetrack that is playable. So once ready, it needs to repair any broken elements, it needs to form a circuit, there can't be any intersections, and so on. Once the designer finishes generating a level, it passes it on to the next component of the system, which is the evaluator. So this is an effect-driven evaluator. It's basically its responsibility is to simulate a session for a target persona. So for example, play this level as a beginner with the emotional responses of a beginner. And it needs to determine, one, the feasibility of the level in terms of gameplay, so that the players can actually go around the track within the time limit. The time limit for these games is set to 2 minutes because of the effect model, which I'll get into later. And it's also responsible for generating a state trace. So it, as it plays the level, goes through, stores the states that it encounters and passes it on to the effect model, which is the next building block. So now, in terms of the affective loop, we're looking at emotion detection. We take the state traces that are generated by the evaluator, and we need to assign the level and associated effect trace. So once, let's say, a beginner has played this racetrack, how do they feel? And we want to reward the designer agent for generating racetracks that elicit a specific target trace. So the target trace can be maximize the intensity of the player or minimize the intensity or have a fluctuating pattern, whatever the scenario that's intended. But once we have the generated effect trace, we can calculate a reward and pass that back on to the level designer. But before I quickly close that up, I just have an example of the evaluator in action. So on the top, you can see a live rendering of the arousal trace and the states that it's producing. And at the bottom, you can see what the evaluator is observing if it were a human player. And on the graph here, you can see blue points correspond to low intensity and red points correspond to high intensity. So you can see it essentially illuminates like the arousal responses of players in real time, which is quite nice as well for debugging and actually exploring the responses of players in generated content besides generating new content in itself. But yes, this loop basically of designing, eliciting, and then rewarding based off emotion is repeated. And depending on what algorithm you're training for your designer agent, you either keep going until you have like an optimal policy that can generate like high quality tracks, or if you're using something like Go Explore, you have an archive of like high performing tracks that suit your task. So in terms of results, I'm going to very briefly go through what we did. Obviously, there's more details about the implementation and the results in the paper, but we essentially compare across 4 clusters of players from our corpus. The corpus is the again dataset for anyone who's interested. The clusters we compare across are all players, so we lump all 107 players from the dataset into one. We have a cluster for beginners who have poor performance, and then we have 2 expert clusters who performed identically, but one were excited, their arousal increased throughout gameplay, and one were unexcited, so they were essentially bored after the race started. And we compare across 3 agents, designer agents. We have a random agent that places random tracks. We have a typical search-based PCG method, and we have our EDRL method. And in terms of design scenarios, we have a scenario where the agent needs to maximize intensity, minimize, and then a very basic fluctuating example where it starts minimizing for 1/3 of the game and switches to maximizing and then switches back to minimizing. And these are just some of the arousal traces of the clusters, just to give you an idea what they look like. So very quickly, in terms of results across all those scenarios, on average, we saw that our approach, being EDRL, outperformed obviously the random agent, but also search-based PCG in 10 out of 12 of the scenarios. And we found that mostly it was the beginners who were easy to tailor content to in terms of circuit design, whilst the experts were a bit more challenging. There were certain scenarios for experts that were easier to generate for, whilst others were proved to be quite difficult. And these are just very quickly some examples, some boring racetracks on the left for beginners with some more high intensity racetracks on the right. And this is just an example of a fluctuating racetrack where you can see the different intensity targets. So in summary, I very briefly showed you how we tackled closing the effective loop through EDRL, and I showed how EDRL can build upon EDPCG with better accuracy and scalability. And in terms of what's next, there are quite a few like avenues of work that this opens up, but one thing would be to incorporate human behavior into the evaluator, because one thing I skimmed over is that we use a simple checkpoint agent for the evaluator, but actually incorporating human behavior might give a more accurate picture of the target persona you're trying to evaluate for. And scaling up to online generation and real-time adaptation would be ideal, as well as looking at other domains. So we looked at autonomous driving before, generating road networks and scenarios for people to learn on or to minimize frustration in road users would be quite nice, especially here in Malta. Yeah, that's it for me. I have a QR code for the paper and be happy to take any questions.
Thank you so much, Matt. And thank you all speakers from the Institute of Digital Games, SASTEC, our keynotes, of course. Just waiting for potential questions here. But yeah, if you're interested in what we do at the Institute of Digital Games, and what we especially do at the OPtiMaL project, then you're very welcome to follow us on social media. We are on LinkedIn, Facebook. We are on, I believe, on X, or we were. Not sure we are still active there, but we have presence, and there will be more news coming out of this project in the remaining few months that they're left. So far, we're very happy with what we managed to achieve, as you see across the two groups. We're very happy that our invited speakers were invited and agreed to come over. Sebastian, Mike, and Vanessa, thank you so much for being around. Thanks to the SASTEC team and to the IDG teams. The recording will be available, so we'll disseminate about this event if people want to hear more or want to repeat some of the presentations. Those will be available. Once again, thanks to Ahmed, Roberto, Marvin, and Sylvie for organizing all this, and the rest of the people involved. And I guess we can call it a day, unless there's like any other last minute comment from anyone.
Yes, George, I suggest post something in chat. I think besides our OPtiMaL project, we also have a task force on PCG. If you're interested in following the updates of the domain, please do join us as volunteers. You can fill in the form, you can contribute to this workshop. Task force. Yeah, thank you.
That's great, a very good point.
And thanks to Ahmed for the excellent organization. Yeah.
Yes, indeed. So thank you all. It's been a long day. Thank you for being here, and enjoy the rest of your day, your evening. Ciao, everyone.